Welcome to our very first lecture on non-chordates. Today, we're going to explore one of the most monumental leaps in the history of life on Earth, the transition to Metazoa. If you have ever wondered why animals are built the way they are, or why we aren't just giant single-celled blobs, you are in the right place. We will uncover the biological secrets and the strict mathematical rules that forced life to become multicellular. Now that we know what we are exploring, let us think about how life operates. Imagine trying to run a massive, busy restaurant entirely by yourself. You have to cook, clean, serve, and manage the register all at once. This is exactly how a single-celled organism, like a protist, lives. It does everything in one microscopic room. But if you hire a team of specialists, a chef, a waiter, a manager, the restaurant runs efficiently and can grow. This is the core idea behind Metazoa. Metazoans are animals, and their defining secret is multicellularity. Instead of one cell doing it all, they have billions of specialized cells working together. Building on this idea of a specialized team, let us look at the formal biological definition. To be classified as a metazoan, an organism must meet strict criteria. First, they must be multicellular and eukaryotic, meaning their DNA is safely stored in a nucleus. Second, they are heterotrophic. Unlike plants, they cannot make food from sunlight. They must eat other organisms. Third, and very importantly, their cells completely lack rigid cell walls. This absence of a wall is what allows animal bodies to be flexible and capable of complex movement. Finally, they typically reproduce sexually and pass through a specific embryonic stage, starting as a hollow ball of cells called a blastula. Understanding these criteria leads us to ask why this evolutionary leap was so crucial. Without the transition to Metazoa, life on Earth would have remained entirely microscopic. Multicellularity allowed organisms to grow much larger, which was a massive advantage for avoiding single-celled predators. It also gave them the physical machinery to travel further for food. Because cells could differentiate, animals developed complex tissues like muscles for movement and nerves for processing information. Even today, studying these early metazoan rules is vital. For instance, cancer is essentially a breakdown of the cooperative rules that metazoan cells evolved to follow. So, we see the benefits of growing larger, but why couldn't a single cell just keep growing? To truly understand why organisms had to become multicellular, we have to look at geometry. A cell absorbs its food and expels toxic waste through its outer surface membrane. Think of this as the doorway. However, it consumes those nutrients based on its internal volume. Think of this as its appetite. The fundamental problem is that as any three-dimensional object grows, its volume increases much faster than its surface area. The appetite outpaces the doorway, creating a strict mathematical limit on how large a single cell can ever get. This geometric limit brings us to the most important mathematical relationship for understanding the origin of animals: the surface area to volume ratio. Conceptually, this formula tells us how much membrane space is available to feed each unit of the cell's internal volume. In this simplified formula, the ratio equals 3 divided by r. The symbol r represents the radius of the spherical cell, typically measured in micrometers. Notice that r is in the denominator. This means that as the radius increases, the overall ratio strictly decreases. If the radius gets too large, the ratio drops so low that the cell will literally starve or poison itself with its own waste. Before we move on, let us see this with a concrete example. Imagine a single-celled protist with a radius of exactly 1 micrometer. We want to find out how much surface area it has relative to its volume. We take our formula and substitute the given radius, r equals 1. 3 divided by 1 gives us a final ratio of 3. Physically, this means there are 3 units of surface area available to feed every single unit of internal volume. This is plenty of membrane space to absorb nutrients and expel waste, keeping the small cell perfectly healthy and functioning normally. Now that we have calculated the ratio for a small cell, let us see what happens if that cell tries to grow into a giant. Imagine a hypothetical single cell with a radius of 10 micrometers. We're asking if this giant cell can survive. We substitute r equals 10 into our formula. 3 divided by 10 gives us a ratio of 0.3. The ratio has dropped drastically. This means there is less than 1/3 of a unit of surface area to support each unit of volume. The cell's doorway is now far too small for its massive internal appetite, meaning this giant single cell cannot survive. So we have proven that the ratio drops as the cell grows using our simplified formula. This brings us to where that formula actually comes from. We are setting out to derive the surface area to volume ratio from basic geometry. First, we define the surface area of a sphere, which is 4 pi r squared. This represents the cell membrane. Next, we define the internal volume of the sphere, which is 4/3 pi r cubed. This represents the cytoplasm. To find the relationship between the two, we simply set up a fraction, dividing the surface area by the volume. This setup is the foundation for understanding the physical limits of a cell. Continuing from our setup, let us perform the mathematical reasoning to find the final result. We substitute our geometric formulas into the fraction. We have 4 pi r squared on top and 4/3 pi r cubed on the bottom. Notice that both terms share a 4 pi, which we can cancel out. We also have r squared on top and r cubed on the bottom, leaving a single r in the denominator. The fraction simplifies beautifully to 1 over 1/3 r, which flips to become 3 over r. This proves exactly why the ratio is inversely proportional to the radius, forcing large organisms to divide into many small cells. Now that we understand the geometric limits of a single cell, let us look at how metazoans solve this by dividing their volume. To calculate how many cells make up a metazoan, we need the standard volume formula for a sphere. Conceptually, this formula calculates the total 3-dimensional space an object occupies. The symbol V stands for volume, measured in cubic micrometers. The symbol R is the radius of the sphere. Because the radius is cubed, any increase in the radius causes a massive, exponential increase in the total volume. We will use this exact formula to compare the volume of a whole animal to the volume of its individual cells. Let us apply this volume formula to a concrete example. We are given a simple spherical metazoan, like an early embryo, with a total body radius of 50 micrometers. We want to find out how much total physical space this organism takes up. We chose the spherical volume formula because the embryo is a sphere. We substitute the large radius, capital R equals 50, into the equation. 50 cubed is 125,000. We leave the 4/3 and the pi exactly as they are for now. This gives us our total body volume, Keeping the constants intact will make our final calculation much easier. Following our calculation of the total body volume, we now need to find the volume of the individual building blocks. We are given that each small cell has a radius of 5 micrometers. Plugging this into the same formula, 5 cubed gives us 125. To find the total number of cells, which we call N, we divide the total body volume by the single cell volume. Notice how the 4/3 pi terms completely cancel out from the top and bottom. We are left with 125,000 divided by 125. The final answer is exactly 1,000 cells. Physically, this means the organism achieved a large size by packing together 1,000 small, efficient cells. Now that we have calculated the math, let us look at what this actually looks like physically. On the screen, you are seeing a side-by-side comparison of two biological strategies. On the left is the single-celled protist. It is one giant circle. The label points out its critical flaw, a very small surface area to volume ratio. Its outer boundary is simply not large enough to feed its massive interior. On the right, we see the simple metazoan, or blastula. It takes up the exact same amount of overall space, but it is divided into dozens of smaller circles. By doing this, every single small cell has its own membrane. The diagram teaches us that multicellularity is an elegant geometric solution, creating a vastly larger total surface area for nutrient absorption. As we wrap up this topic, let us reinforce the most important ideas we have covered today. First, remember that metazoans are simply animals, defined by their incredible strategy of multicellular teamwork and specialized cells. Second, we proved mathematically that a single cell cannot grow infinitely large because its volume outpaces its surface area, leading to starvation. Third, by dividing a large body into many smaller cells, metazoans successfully bypassed this strict geometric limit. You have now covered the fundamental reason why complex life exists. This single evolutionary leap is what allowed animals to grow large, develop complex tissues, and eventually conquer almost every ecosystem on Earth.